Hello everyone, my name is Luis. Today I'm going to talk about my ECE 570 project, which is called Extending Word Embedding Vocabularies Using Bag of Subwords. So before I actually delve into the details of my project, I wanted to sort of give an overview of what was happening with word encodings before 2013. So if you had two different words, you would basically encode them as two different one-hot vectors. A one-hot vector is being a vector which has values all zero except for one entry. So if two vectors have the one entry in a different position, that means that they have two different meanings. The problem with this representation is that it's very hard to extract the meaning between those two vectors. For example, if we have dog represented like this and cat represented like this, we might know that dog and cat are different because they have different representations, but we don't have any idea about the similarity in the meaning of those words. So this is where word2vec comes into play. Word2vec uses the idea of distributional semantics, which is that words with similar distributions or words occurring in similar contexts have similar meanings. So it uses this idea to train a model over a very large piece of text, which in NLP we call a corpus, to produce a dictionary that maps a word from the corpus to its embedding. And the embeddings here are 300 dimension vectors. The result is a vector space containing the embeddings of all words in the vocabulary. And if two words are located near each other in the vector space, that means they tend to have similar meanings. Word2vec was extremely successful, but it does have a few drawbacks. One of the main drawbacks is how to deal with out-of-vocabulary words, which is basically how to generate a word embedding for a word that is not present in the original corpus. You might encounter a lot of out-of-vocabulary words when you have typos or new words embedded in social media, for example. So for my project, I chose to re-implement the bag of subwords algorithm, which was developed by researchers at the University of Wisconsin in 2018. So the main idea of this algorithm is to address the out of vocabulary problem by looking at each word as a collection of character n-grams. And character n-grams in this case are just substrings. Given pre-trained vectors for a vocabulary, such as the output of an algorithm like word2vec, and then given a word that is not present in the vocabulary used to train word2vec, you can actually train another model that can break down the new word into its n-grams to generate the embeddings for the entire word. So now I'm going to give an overview of the bag of subwords training algorithm. So with bag of subwords, the embedding of a word is simply the average of the embedding of its n-grams. So that's basically what this first formula is saying here. For every word, we're going to calculate its n-grams, which is basically this symbol here, and for each n-gram, we're going to take the word vector for that n-gram, add them all together, and divide by the total number of n-grams for a word. That is the word embedding according to our model. Now we have to actually get the embeddings for these n-grams because those embeddings aren't given to us. All we have is the embeddings for the words in the original vocabulary. So we try to minimize the loss between the generated and given vector for each word. So that's what this formula is saying. This is what we're trying to minimize, where for every word in the given vocabulary, we're minimizing the loss between our bag of subwords embedding and the actual embedding. And here the loss is just the mean squared loss. Now let's talk a bit about the results. The model is simple and fast to train. Training the model over 100 epochs to generate n-gram word embeddings given 160,000 pre-trained vectors took about 55 minutes on my laptop, and in total it generated a dictionary that maps about 550,000 n-grams to their respective embeddings. I also ran word similarity tests on the Stanford Rare Word dataset, which shows that my implementation's performance in word similarity tests is in line with the original implementation, and just a bit below word2vec, but word2vec did find 162 words that it could not find an embedding for, and that's exactly where my model excels. I also ran analogy prediction tests to illustrate that my model is good at understanding the relationship between a word's substructure and its embedding, but it does not understand semantics well. So this analogy prediction test shows exactly that. It performs far better in morphosyntactic analogies, which are of the type amazing is to amazingly, as surprising is to surprisingly, rather than country demonym tasks like France is to French as England is to English. My last test shows that my model is robust to misspellings. So basically, misspellings are one of the greatest sources of out of vocabulary words. And as you can see, the cosine similarity between the misspelled version of a word and the original word version of the word is fairly large, and it only tends to increase as the number of characters increases. And that's the end of my final presentation. Thanks for watching.